CTO and the creator of the company, Shay Banon. So let's welcome him.
Hi, everybody. Meetups, what I found to be very, very successful is just to have a very open-ended QA. I can do presentations, but I can also do whiteboards or something along those lines. I guess I'll start with how many people here use Elasticsearch? All right, cool. How many people here use Lucene? Well, if you use Elasticsearch, you use Lucene as well. Okay, cool. As was mentioned, I was the one that wrote the first few lines of Elasticsearch 4.5 years ago, something along those lines. It's no longer only me, which I'm very happy. And I guess we can start. Let's start with some generic questions, and then I can come up with questions if there aren't a lot. So yeah, any questions? Anything related to Elasticsearch, Lucene, anything along those lines? Yeah.
What was your reason? What was missing when you created Elasticsearch? What was from the ecosystem?
Sure. So why Elasticsearch was created in the first place? So I guess my background counts a bit towards that. I was doing search, never professionally though, which was very annoying to me. I always tried to do it, but I never managed to. But I was doing it on an open source side. I developed a library on top of this thing called Compass. How many people here are Java developers? So the idea was it's like a hibernate for Lucene. And what I saw, that I was super surprised. I was living in London back then. I remember like the moment where it hit me was when I was talking to UBS and they were like indexing trades using Compass, which I thought was, why would you want to do something like that, right? But they found the ability to express search requests, queries on top of Compass or Lucene effectively to be very liberating when it came to actually trying to explore data. Actually, when they put that application in front of traders, they suddenly could, search through trades in a way that they could never do that before. And back then, even Compass didn't really have any analytics capabilities to it, so they did like very simple counting around it, which obviously makes a lot of sense when it comes to trades. And then I started to see it a lot, that what you would think about like a search technology or inverted index, it's just being used in so many different cases. It applies to so many different cases. And as time passed, search got really bad rep, right? I mean, I remember when we started the company, we said, should we call it Elasticsearch? Like, are we, is search the right term for it? And I personally believe so. Like when you try to search over something, you're searching over it, whether it comes back as a graph or whether it comes back as heat or something along those lines, it doesn't matter. And the reason why it got such a bad rep was that the focus of search was how quickly can I index SharePoint and parse PDF documents, right? And that was funny, and it was very, very frustrating to me seeing those things happen. That was, there's tons of data out there. Why focus on PDF documents and Word documents version 5 and 6 and 7? And that was driven mainly by enterprise search companies, right? Back then at the time. And then the big data movement started to happen. NoSQL started to happen back then. I was working at a company called Gigaspace that was doing distributed in-memory data grid. Had a lot of experience there trying to solve complex problems, low latency, what have you. Obviously competing with very, very interesting companies like Coherence and Terracotta and other very, in the front out there trying to solve very complex problems. And the thing that so there were two angles to what I saw back then when, I was thinking about Elasticsearch way before I wrote the first line of code. I knew what it means to try to be on top of a successful open source project, and I said it took me like half a year to gather the courage to write the first line of code of Elasticsearch. So there were two aspects to it. The first one, obviously, I think that was the last time I actually looked at Solr. But back then, I just took a very deep look into Solar and to understand, like, am I going to develop something that is meaningless, right? This Solar is good enough and it's going to solve the problem. I had no idea. And when I looked at Solar, there were a few things that bothered me, and also I looked at it in terms of the history of it. Things have changed. A lot of features were copied, but I think that when you develop a successful product, you have to have you want to build something that users end up being to a degree enriched by it, right? You want to have a lot of empathy to the users. Either it comes through API, it comes through what does it, the hell does it mean to manage that project? And I didn't feel that empathy in Solar itself. And even Solar would have copied feature X or feature Y, would have fixed one thing or another. I didn't really see it happening. I saw it in Lucene, definitely saw it in Lucene. But on the Solar level, which are like effectively two completely different development groups, I didn't see it, and I didn't see it happening. The other aspect and it also ties a bit into my history. So, for example, when I joined Gigaspaces, one of the major refactoring efforts that went in Gigaspaces when it came to actually building larger clusters was to change the core architecture of it to be completely evented. And I think it took us, when I joined, we were just moving to NIO, and it took us another 2 years to actually fully finish that transition. That's like a commercial company that has full-time developers working on that had like a clear goal. And this is like a long arc for a project that was built not to be evented, to be evented. And this is one aspect of building a good distributed system. And when I looked at Solar, it was built from the ground up to be a single server solution with slave. Like, I don't know if I'm allowed to say slaves anymore, but with whatever followers. And ripping that out is huge. And this has to be in the DNA of the developers. Like this, they really need to care about it. And it didn't seem like the developers really cared about that aspect. So in Elasticsearch, for example, when you execute a search request, the fact that you're going to hit 100 nodes has no effect on the resources in terms of networking. It's something special. But when you build something like that, and if you just look briefly at the Elasticsearch code base, you see a lot of callbacks and evented and things along those lines. You have to go all the way down to the NIO layer and expose it all the way up. In our case, we use Netty, but it doesn't matter like what you use. And don't be fooled by people saying we use Netty, yet still do blocking, right? I mean, at the end of the day, when you execute a search request and you're waiting for the response and you're solving that thread, it doesn't matter. You can use Netty, you can use something else. You're still doing blocking IO. It's still blocking those threads. So that was like just one example of what it means to build up like a proper distributed system that was just missing. The other part was that if you look back then, the systems like the NoSQL solutions that were being built require a big quite of a mind shift to try to understand how you're going to do something with your data after you put it into it. The only one that did it was MongoDB. And I think this is the biggest reason why MongoDB was successful. It just has a very rich query language. And at the end of the day, you can build the best distributed data store out there. If you put your data in and you're feeling frustrated that you can't do anything with it afterwards, it's a fail. It doesn't matter, right? I mean, you as a developer want to put data in and then feel like, okay, I can get something out afterwards. And search is a wonderful technology to do it, like Lucene and queries and things like that. And the only ones that were close were MongoDB, where they relied on B trees and all the baggage that comes with B trees. Not that it's bad, it's different. And this is, by the way, one of the fascinating things that people don't realize. If you take things that are like B tree based, in Elasticsearch, if you index a JSON document that has 150 attributes, by default, all of them are indexed. Like think about creating a database table with 150 columns and putting an index on each one. It's going to kill the database. And then what's more interesting is that regardless of whatever combination of those attributes that you're going to query base, those indexes are going to be fully effective. So even if you go to a database table and put 5 indexes, and then you query those 5 attributes, not all of those 5 indexes are going to be used. If traditionally you would, will pick one, if it's smart enough, it will pick the correct one, and then the other ones will be full scan. Some can be smarter and use 2 or 3, but like there's a limit, just by the nature of how things work. Nothing bad with how they implemented it. It's just life or math or what have you. And with how the inverted search engine works, you can just make use of all of those. So you have that freedom of executing those search requests, and actually they're going to come back quickly. So all of that together just made sense to have like a proper distributed, with a lot of empathy to users about what they're trying to do through APIs. And when I say empathy, what do I mean by that? When we build the facets, which are the predecessor to aggregations, we could have said, okay, here's a generic form, write Java code that gets deployed, that's MapReduce, we're doing scatter gather, and go break your brains about what you want to do. And we didn't. Like what we did is, typically what you do is draw a graph or a histogram that shows, events per day or something along those lines. Here's one built in. Go ahead and use it. This is the part about the empathy. If you're good enough to think about how your user uses your system and how well your system works in the context of the user, you can actually build built-in components and they don't have to work too hard to get it. And this is like a very strong concept in what we try to do. And you see it through our APIs, and sometimes knowledge leaks, right? You might see things like stupid backoff true or false, and then you have to go and figure out what the hell is stupid backoff. But we have some defaults that make sense. So it allows you to keep things on a very shallow level, but still get a lot of value, and still be able to go deep all the way to the Lucene level or other algorithms that we're running and affect them. So yeah, and the funny thing is, by the way, when Elasticsearch was created, I knew what was going to happen, but it's not because I'm super smart. It's because I saw what was going on with Compass 7 years before, and I saw how people were using it on a single node case. And the fact that Compass was so generic, like it didn't have a go and index documentum type of component to it, that people, and it's just like, here's my business logic, or my objects going to index it, actually helped realize what can be done with search, because I saw all of those use cases. And it was very evident to me that once facets were added and other features were added, you can use it for time series data. You can use it for many, many different use cases except for your traditional relevancy-based searches. And that eventually started to happen. But that was a lot of effort that came from myself, other developers. For example, even before Jordan joined our company, but even before, I was on the Logstash IRC all the time, trying to listen. What are you trying to do? What doesn't work? Oh, you keep on creating index per day. That's great, but you need a template. I'll go and create a template mechanism so you don't have to redefine it each time, right? So all of those things, just listening to your users and making sure that you implement the right things. And the last bit is just say no to complex features. So for example, you won't find features in Elasticsearch that don't work in a distributed environment. And there was a lot of pressure, especially at the beginning, like why does this have this feature and you don't have that feature, and why this has that feature and you don't. And part of it was education, just explaining, this is not easy to implement if by default you're distributed. And we don't want it to break. So for example, things like field collapsing that you have in Solar is only going to come in 1.3. And we had to build a year and a half based on infrastructure that people don't necessarily realize in order to properly implement it in a distributed environment. It's the same thing with, what was the other example? Spell checking. So if you go to Lucene with spell checking, you see that up until Lucene 4, you had to create an auxiliary index in order to do spell checking. I just refused to add that feature. It makes no sense. Like Elasticsearch needs to be real time. If you need to rebuild your spell check index, whenever you change something, this is like not usable. Luckily, there's like super brains in the scene, and they figure it out. And even more, luckily, they work with us now, so we can have them working on that full time. And that's how we like to do things. Like we won't implement something that doesn't adhere to our core values. You know, another example is suggestion, as you type suggestions. We didn't implement it until we could implement it in real time or in near real time. It's very easy to implement it in non-real time case where you have to rebuild the index every time, and you build this optimized data structure that does it. It's not simple to do it for data that keeps on changing, yet you still have that capability. So we will not implement things that don't follow what we believe in, so we can keep our product, you know, consistent and at least expose some sort of consistency across the APIs and the behavior. That was a long answer. Yes.
So Elasticsearch is like one of the most successful open source projects.
Yeah.
So I'm wondering like how you make it so successful. What are the key lessons? And also in the initial stage, how you like attract the first couple of committers to your project and make it bigger and bigger.
Yeah.
So yeah.
Good questions. I'll start with the second one because it's simple. Up until we started the company, I wrote 99.9% of Elasticsearch.
But how you compete with, or like it's like you have a daytime job or?
Yeah. Actually, I quit my job to do Elasticsearch full time. And you know, I was lucky enough to have a family that supported me with that decision.
How long you like?
I was without a job.
To reach like 1,000 stars.
To reach what? Sorry.
To reach like 1,000 stars in your GitHub, like or your first 20 committers. How long does it take you to go there?
Yeah, I like 20 committers in Elasticsearch were rather quick. But the patches were light, and it's not because the committers are not good enough. It's a complex project. Even in the first release of Elasticsearch, right. You know, when you just open up Elasticsearch in the IDE, it's frightening.
Right. So that's like so curious how you got so successful, because it's a very complex thing, right? You need a cluster set up.
Yeah.
But how you can do by yourself without much support, but you gather
by myself.
Like your initial stage.
Yeah. So. The first thing that you realize is that when you're building distributed systems, actually you can simulate distributed systems on your laptop 99.9% of the cases. And this was one of the first things that were core to what Elasticsearch was developed, and now it's like light years ahead, was to be able to run tests and be able to spin up clusters within the JVM. And you know, if you look at typical Elasticsearch test case today, you'll see tests that are spinning 5, 6 nodes, shutting them down, all of those things. So any problem that a user has, we can simulate exactly the same problem now within an integration test that run in a single JVM. So we can simulate network disconnections, we can simulate failed hardware. We actually have tests that are like, we call them evil tests, right? That just throw exceptions when you try to read from a file or something along those lines. A lot of it came from Lucene, by the way, a lot of that infrastructure. So first of all, when I'm a single developer, yes, it's like people were using Elasticsearch on 50 nodes, and I would go, oh great, because I tested 50 nodes on my laptop and it worked. Well, it seemed to work, so I don't know. Obviously, there were growing pains. There were a few companies that made a huge bet on Elasticsearch, and I was helping them. Like I was another employee in those companies effectively at the beginning. So they were making huge bets on Elasticsearch. They contacted me privately, and I was working with their engineering team all the time. Like I had the Skype groups for each company, and I was like helping them all the time to make sure that things work well. And they were better, they were testers. Like they were testing Elasticsearch under massive clusters and making sure that it works. And when things failed, and they failed, I would make sure that I have the test for them and develop it.
So how hard for you to attract those companies, because they are kind of your customer, your initial customer?
Yeah.
How hard for you to attract them, or they just come by because your product is so awesome?
Well, it was a combination of there was really nothing out there that did it. together with the promise of Elasticsearch. So if you even from the beginning, like it's funny, like if you go to the video of Elasticsearch in the getting started part, and you hear me like typing like crazy on the keyboard, that's the video that I recorded when 0.4 Elasticsearch was released, and it still works today. So the vision and the APIs and the cleanness of the APIs and all of those things, those things that attracted the early users. They saw the potential. And that together with the lack of competition.
So you're being very innovative, right?
Sorry?
I mean, nobody else done that before.
It's hard to say like whether someone did it. Nobody built a distributed system, even in the early releases, at that level. The closest that you could get was trying to do something with Solar, but that involved a lot of craft back then. Like you had to static clusters, and the replication was segment based and not action based. There were a lot of different things back then. Since then, Solar has caught up in some of the features, but yeah. I think at the end of the day, why Elasticsearch became successful is because it solves the problem. And I didn't wake up one morning and said, oh, there's a problem, I have a solution. This is like 15 years of history of me dealing daily with a Compass. At one point, I was coming back from my day job in London and doing Compass all night and all weekend. And a big portion of it was just answering questions on the mailing list, not even development. So I got all of that knowledge that then ended up being translated to Elasticsearch. So I won't even look at it like in the past 5 years. I will look at it in the past 15 or 16 years. Yeah.
So can you tell us a little bit about the sort of the interconnect of design principles of the the sort of the cluster work? How do they communicate and all that?
Yeah, sure. It depends which version, but at least now. The way that it works is effectively when you fire up Elasticsearch, all the nodes have all the roles. Effectively, and we'll get to the roles afterwards. And when you fire up Elasticsearch, there's a very simple, we call it a ping process or a discovery process, effectively, that tries to find other nodes in the cluster. A cluster has to elect a master, a single master, and that master is effectively responsible for cluster level events. So if a node joins, it will only actually join the cluster after the master has said, okay, you can join, right? If you go and create meta level operations in Elasticsearch, like create an index, then it has to go through the master because there has to be a single consistent view of it. Just as a side note, I think that one of the breakthroughs that I had at the early days of developing Elasticsearch, if you think about it, that the master needs to maintain this cluster state of which indexes are there and which nodes are there and so on. And the early code base had all of these events coming in, and then we tried to build like a concurrent system that tries to deal with concurrency and when do you publish it and things along those lines. One of the breakthroughs that actually simplified the code of Elasticsearch completely was to serialize it. So every time there's an event that comes in, they go into a queue, and you pick up the queue, those events one by one, just apply them, and republish it, and so on and so forth. And this has simplified the code tremendously. I don't think Elasticsearch would have been here today if that decision was not made at the beginning. And it's a known design pattern. It's not nothing that we invented or something, but that was a big breaking point in the Elasticsearch design. So after the ping discovery, master election, and so on, the master election today works very similar to something called the bully algorithm, which is each node, when it starts, has a funny name, but that's meaningless. It can have the same funny name across the nodes. We generate a UUID for that node, internal UUID. And we pick the lowest UUID. And when a master fails, then another node will get elected because it has a different type of UUID. We have a bug there that I can talk about if you want, and how we plan to fix it. One of the interesting things with building a distributed system is that you find that the reason for pains in a cluster, most of the time don't come from what you expect them to come from. So for example, when you're talking about disconnects between two nodes, the first thing that you would say, oh, my router is down, or the network got disconnected. Most of the time, that's not the reason why nodes disconnect. It's because someone executed a request that takes a lot of memory, and you're running into GC hell, and this node doesn't die, but also doesn't live. Really, this is a quasi state. And this is by far the biggest reason why you would see things like disconnections between nodes in Elasticsearch. So for example, in the past few years, one of the biggest investments that we made, and it's not necessarily very visible as a feature, is how do we manage that memory? And how do we properly allocate memory? And it doesn't even come from, we have circuit breakers that if you try to allocate too much memory, we'll just refuse that request, and we try to predict how much memory it's going to have, and we keep on adding those circuit breakers. It doesn't even end with that. It's also like understanding how Java garbage collection works. One of the biggest reasons why Java garbage collection problems happen, it's because you just generate too much garbage that it doesn't fit in the young generation anymore. And then you get young objects going into the old generation, and someone else has to clean it up, which you don't really want them to clean up, young generation. Because typically young generation objects are small and very fragmented, it has to run compaction eventually, like the old generation. So those type of problems, we think about those. So if there are like a lot of the memory data structures that we allocate, it's like just allocate batteries, all the way from the scene to Elasticsearch, and we reuse them if we can, just to make sure that we don't have to allocate them all the time, over and over and over again. So those are a lot of things that we do in order to create cluster stability. Now, with all the bugs in the world, if 99.9, like if 20% of your cluster instability comes from Java memory pressure, and you've just removed it, you've just improved the stability of the cluster. So the way that we look at those problems is we're helping customers today that run 10, 20, 30, 50, 100 nodes. What do we see that cause problem? And this is what we're going to fix as quickly as possible. Theoretical problems are nice. Do we really see them in practice? And then we simply prioritize based on that. I don't care about what everybody else says. If we see problems that occur more often, we're going to fix them. If we have more resources and more people, and we're happily, one of the things that we don't say, by the way, is if you have a problem, it's open source. Submit a patch. I think that this is like the worst response ever by open source developers, right? It's like, I hate it when people say that. It's like you take a lot of responsibility when you open source projects, right? And GitHub made it really, really simple, and it's like irresponsibly simple, if it makes sense. Like people depend on your code. You have to take responsibility for it. And this is why it took me a long time to create Elasticsearch, because I knew that I'm taking responsibility now for people betting their applications, their startups, their businesses on top of the system that we're building. You have to be there for them. So we're on top of it. We're gonna fix it. If you want to help, that's great, and we will help you to help us, but you don't have to.
Just a follow-up question. So like the first part of the infrastructure that the master selection, or just the master be able to sort of control the entire cluster, sort of overlap with something, Zookeeper and all that.
Yeah.
Do you have any sort of intent to move to something so that you can sort of based on some more standard and more I don't know how much traction that Zookeeper has.
Sure. Well, first of all, Zookeeper is wonderful. It's a good piece of software. It works really, really well. When Elasticsearch was created, actually Zookeeper was around. Actually, the first version of Elasticsearch didn't even have its own discovery mechanism. We used JGroups. I don't know if people are familiar with that at all. One of the problems that I had with JGroups, except for the fact that it didn't work, was that what is a live cluster? A live cluster is a cluster that keeps on sending requests. Like if you look at the raft algorithm, something along those lines, a big portion of what does it mean for a node to be alive is the fact that you keep on sending requests over it. And what I saw with JGroups was just two network stacks. There was the network stack of Elasticsearch that was based on Netty, Evented, and all of those. And then there was the network stack of JGroups. The fact that there were two just created this disconnect. Like JGroups didn't know about something that was going on in the network stack in Elasticsearch and couldn't act based on that quickly enough. So I think that, so this is one of the reasons why us implementing our own discovery algorithm that uses the same network stack that you have to execute search requests and everything, we still have pings, but effectively every time you execute a single search request or something along those lines, you're pinging at the nodes, whether they're alive or not, right? And we use that function, and it helps building a more, a better stability system around it. I agree about the not, there's the notions of not invented here or something like that. It's partially true with Elasticsearch. I think a big reason why Elasticsearch is successful is that it's easy to operate. And if I'm going to come back now to the users and tell them, now you need to operate 3 zookeepers, you have to understand how the GC performance works in Zookeeper and how do you allocate, disk and things along those lines and what have you, and the stack and the ports that needs to be open and ensemble, and what happens when you want to do a rolling restart with Zookeeper. There's tons of suddenly complexity involved, right? Which you don't have it with Elasticsearch today. So I think that the fact that we're taking the overhead of actually implementing something that will work good, and hopefully to the same level of Zookeeper. Like we have the infrastructure now to make sure that things work correctly, and we're going to fix the bug that we have. Is actually worth it to our users, right? It's just going to make their life simple. And the last thing that I accept is don't implement that because you can't. I just don't accept it. Like there's well-known algorithms. We're going to improve what we have. We have people that are smart. They're going to implement that algorithm and make it work, right? If someone else did it well in Zookeeper, that's great. Someone else is in another system, that's great. We can do it as well.
So, like on that note, what is the largest Elasticsearch cluster running today? Like, can you
So I'll just finish the thoughts about your question about the roles. What we did in Elasticsearch, which was a change to move it into more of a Zookeeper type deployment, is that we allow you to have dedicated master nodes. So as I mentioned, one of the reasons why things fail is that you overload the networking stack or system, just resources-wise. So if you have dedicated master nodes that don't accept searches, don't have to deal with indexing requests or crazy operations, and you have a more stabilized, the stability of your cluster is going to be much more enhanced. And I recommend running dedicated master nodes. They're super simple to run, right? That's the nice bit about it. It's just another node. You don't have to change your infrastructure. It's exactly the same Elasticsearch nodes and how to run it, and same ports and what have you. It's just another role. The biggest cluster that I'm aware of depends between 150 and 200 nodes that I know for sure. I heard of bigger clusters, but not tremendously big, not like a 1,000 node cluster. I would say that a 1,000 node cluster in any system is probably a mistake. I think that managing a 1,000 node cluster is not easy, and if that cluster is down, 1,000 machines are down. So as you grow, to 100 node cluster or something like that, I would start creating multiple clusters. It just makes more sense. It's like another layer of protection when it comes to some area fails in your infrastructure, then at least it didn't affect all of your users. Bad things might happen. We try to fix as much as possible, but they still might happen. And the question is how, what big of a proportion of your user base is it going to affect? What we did in Elasticsearch is that we added this really nice concept of tribe node. So even though you're running like multiple 50-node clusters, you can put those tribe nodes in front of them and make it feel as if it's a single cluster. So that's like if I would envision architecture that goes into Elasticsearch to the 1,000 or 5,000 nodes deployment, then I would see like pods of 100 node clusters with potentially tribe node in front of it.
Same extension
Yeah.
to that, how big of a index have you seen in
Yeah.
larger sizes?
Well, I've seen petabytes of data stored in Elasticsearch. Definitely. And how fast were the searches? Depends. Depends on what portion of the data they were searched. Because it's interesting, right? I mean, this is one of the nice things about Elasticsearch. It's like we see so many different use cases. And one of the challenges that we have in Elasticsearch, which is different than other systems or some systems, is that we have such a rich API, such a rich way of querying and aggregating and things along those lines, that that just the breadth of use cases and different ways of users using the data is quite different than a system that does, key value pairs or something along those lines. It's just a different scale of problems. I'll take key value pair building a distributed key value pair any day. Right? It's simple compared to just I have to deal with fuzzy queries and highlighting and those type of very very complex interactions that we have to deal with daily. And that changes the game, right? I mean, you can see systems that care more about just having massive amounts of data, but searches are not often, compared to having massive clusters that have small amount of data, but a huge volume of search requests, to time-based data that only today's index is so hot that you have to care about it, but yesterday's index is no longer relevant. It's different, very, very different use cases. Yes.
What's the fastest rate of data intake that you've seen?
Fastest ingestion rate. What was the 100 or 200K? Approaching 300K documents index. It scales well. So as you add more nodes, you'll get better indexing ingestion rates. And we're continuously working on improving that. Like 1.2 has very nice improvement when you rely on Elasticsearch auto generating the IDs to improve the indexing rate. Annoying slowness in analysis chaining Lucene are being fixed all the time. Not that we have people that work on it all the time. It's funny when Mike and Robert joined, they said, we didn't know that indexing mattered so much. They were fully focused on search, like how to make fuzzy query faster, jump query lookup faster, those type of things. I said, okay, it doesn't matter if indexing is slower. But then when they joined Elasticsearch, they saw that the time-based data, like I have tons of events coming in all the time. Like we care deeply about indexing rates. And you'll see a lot of the work that has gone into the scene in the past few months is focused on that. And they're great developers. It's just a matter of the same thing that I had, right? Just put in front of you how people use your system and go work on fixing that and improving that. Yes?
Would you comment on what type of applications is best suited to build on the Elasticsearch versus many of the others who's trying to say they also get a search platform?
Search compared to other systems that have search
or some type of search capability. They may not be a full-fledged search. Sure.
So if you care about, I'll start with, if you care about unstructured search, then you have to have something that does it. Like you very quickly outlive things that have been added as an add-on. Like you can't go to MySQL and use MySQL full text search, or Postgres with Postgres full text search, or other systems that just they're great at what they do. That's not what they do well. So a lot of times I see people just starting with us because you just have unstructured data that they need to search on, and there's tons of structured data next to it. So they go to Elasticsearch and then they'll do the unstructured searches part. So this is one reason why I would go to use Elasticsearch. So you have even a tweet that has 140 characters, that's unstructured data. So if you want to search across it, that's something that you would use Elasticsearch for.
So you're saying that Elasticsearch is for both structured and unstructured search?
Yes. Yeah, definitely. So I'll start. You start with the easy answer is if you have unstructured data, you probably need something like Elasticsearch if you really want to do something with it in a sophisticated manner. And then the question is, how can you? And then you'll start with how do I combine unstructured and structured together? So even if MySQL has a good unstructured, not good, but acceptable unstructured search support, when you try to combine it with structured search, it's slow, right? It can't be tree and how the whatever they built there works. It's not going to work. And in Elasticsearch, more specifically in the scene, it's the same thing. I mean, if you think about structured search in the scene, it's just an untokenized token, right? Just take the text that it is and treat it as a single token instead of taking the whole text and breaking it into tokens. With exceptions of numeric values, there's a try thingy going on there, but they're work well as well. And then that combination works really well. And what I've seen happening is that a lot of times, the database ends up being slow. By the nature of database having to be, ACID, and if you have high ingestion rate, then you start to fight off the performance of rebuilding the B tree and making the indexes available to, decent searches. I do see a lot of cases where just structured search start to move to Elasticsearch. And there are compromises, right? I mean, Elasticsearch is not fully real time. Get by ID is real time, but a big part of why the search is fast is because it's near real time. So every second it gets refreshed. So this allows your scene to do optimization that you just can't do in other systems. The other part where Elasticsearch really shines, I think, is that we invested a lot in the analytics components, what we call them aggregations. Effectively, we've built an in-memory database as well. So if you look at how we work with aggregations, all of the time that we spend into optimizing those specific use cases, those are things that they're not as expressive as SQL potentially, but for those dedicated use cases, we optimize the hell out of it. And people find the ability to do unstructured search with structured search, and on the resulting group run aggregation to be very liberating when it comes to them trying to figure out the data. And the part about liberating, a lot of times what I saw is that you get to the level where you can actually put it in front of your users. If you're building an application, you find yourself without intending to putting a graph and putting a search box on top of it. And as users type, suddenly the graph changes. Even if it's billions of documents, the graph changes to reflect that. It's mind-blowing to users, right? I've seen startups just based on that, conquering the market. Because it is impressive. And it starts from I don't know, social media type analytics. I don't think there's a single social media company now that doesn't use Elasticsearch. Right? It's just from that to many different applications that use those systems. And then the interesting part that it gets to the point where I see a lot of cases now that there is no unstructured data. There's just a lot of structure and aggregations. And the fact that you can have 150 attributes and slice and dice the data based on any type of aspects of those attributes and then aggregate based on any aspect, that's something that it's very hard to do in other systems. Yeah.
So there are a lot of people using Google Analytics to monitor the website. Is there a way to make better than that with Elasticsearch monitoring in some way the queries and the responses to get even putting everything on the stack and getting a log stash real-time view of what's going on with the searches?
I won't say better. I think there's things that you can do with Google Analytics that you can't really do with Elasticsearch. They do some very advanced things because they know that they're going to monitor websites, and they do Google Analytics, so it's very highly specialized for that. I've seen cases where people didn't use Google Analytics, whether because Google was a competitor or because of other reasons, that you just use Elasticsearch and the Elk stack to build something like that. But most of the times, actually, the reason why people did it is because they could tap in other data sources that would help them understand what happens in their website. So for example, if you take all your Apache web logs, it's great, use Google Analytics, but take all of your Apache web logs and then take your application web logs into Elasticsearch, and then take some metrics from your system and also put it into Elasticsearch. You can actually answer questions like, this web page is taking too much CPU because of this application error code. That's not something that you can easily answer when you use different type of solutions.
But if we focus on just on improve the search, understand the most popular searches and how I can get better results. What's the best way of doing it?
So I'm not sure. I think I answered a completely different question. What do you want that?
So if you want to monitor the searches that people are doing on their website,
yeah,
right? And then match it with the responses and check how the queries are going. So this is the response terms, and this is the response term.
Yeah. That's not something that is built into Elasticsearch. The ability to have this feedback loop from executing a search, how well it matched, and then the next time you execute that search, if it matched well, then rank it higher.
Exactly.
Or even clickstream, like if the search result ended up returning the results the second, I guess the second or third item, but people keep on clicking on it, it might make sense to push it up. It's not part of the stack itself.
It's kind of hard to do with the log, right?
Yeah, you'll need to build something dedicated for that. I've helped companies do something like that on top of it using Elasticsearch, but they were like very advanced in how they captured all those access logs and everything, and then replay that clickstream or those search requests back and affect the scoring of results as a result of that. It's possible to do it in Elasticsearch. You have to roll down your sleeves and develop it today. We have ideas or very in the sky type thoughts about how do we create it as a feature in Elasticsearch, but it's not in the immediate roadmap of what we try to do. Those type of things are so open-ended that it's a lot of time when it's open-ended, like how do you take this big problem and make it digestible to users, right? Yeah, if you manage to find a way to do it, this is an interesting topic that we keep on spending cycles as in brainstorming, but not actual code. If we find a way to do it in a digestible manner, then it will be in Elasticsearch.
Because when they find mapping and everything, you're like just doing guesses, right? What's best for search? And the improvement is kind of an interactive process.
I completely agree. Yes. Yeah. If you really want to build a system that takes relevancy deep into its heart, then you have to have this feedback loop of okay, so how well our searches are doing, and then take that back into your scoring model. Yes. Yeah.
Can you talk about data integrity in Elasticsearch? I've built my whole product based on Elasticsearch being the sole database, and I know you wouldn't like that. It's also on the cloud.
Yeah.
And you try to focus a lot on snapshot restore. And things, but can you talk more deeply about?
Sure. Well, yeah, I think that it takes a lot of responsibility to say that we are a data store, and we don't take it lightly. And I wrote a whole blog post about it. I don't know if you saw the Resiliency in Elasticsearch, and we've seen it's on the Elasticsearch website. And there's a few things that I miss on the scene level, especially when it comes to checksumming. So Robert actually already added checksumming of all the files in the scene. And the small ones are being checked during merges, so we can detect corruptions. And we're working on the bigger ones, and there's still work left to be done there. So aside from that, there's many different aspects of the Lucene level, the store level that we need to improve, and we're working on that. Like it's not that it's bad, but if we're going to say we're a data store, it has to be there. Very simple. And then there's the Elasticsearch side. There's a few things there. Obviously, there's the bug with the master election that we need to fix because that can cause data loss. Or you need to pick what you're going to do in that case. There's another one that is more tricky. I don't remember if I wrote about it in the blog, but today I don't know how many people like. If you take a cluster, shut it down, and bring it back up, sometimes it very quickly becomes yellow, and then it takes a long time to become green. And the reason why it happens is that we're not smart enough in trying to detect whether we can transmit deltas between a primary and a replica. So if there's any type of discrepancy, we'll copy over segments of the scene, and that's going to take time, right? Just by the nature of networking. But with that, without checksums, we can actually migrate corruptions. So if you don't know that the data is corrupted and you suddenly copy it over, and you just migrated a corruption. So this is something that we're also working on. So to make sure that we have a very good way to detect deltas between and then replay them, so we won't migrate corruption. So both verifying corruptions in an optimized manner and making sure that we detect them as quickly as possible. And when I say corruption, I mean like low-level, disk-based corruptions, right? A bit has been thrown out for some reason. I would feel more comfortable if that data is important that you can index it. I don't care, store it as flat files or something like that. Somewhere on S3, doesn't matter to me. But in a lot of cases, people store the data in Elasticsearch, and that's okay if data gets lost. I haven't seen a lot of cases where data actually ended up being lost. And we work very, very hard for it not to happen. We just don't feel comfortable today to say that you can use it like as a data storage. Sorry. And by the way, the funny thing is that regardless of whether we say it's a data store now, those are things that we want to fix, right? I mean, if a user has 1 petabyte of data in Elasticsearch and they lost that data for some reason, it's going to take them months to index it potentially. So, I don't want them to go through that process regardless of whether we're a data store or not. Yeah.
So you were talking earlier about the architecture of the distributed system that you were building early on. Like, what thoughts went into whether you decide to add node-level cache or distributed cache to make the zookeeper type decisions that you were saying about leader election? Or I know this is a very general question.
Yeah, I'm not sure.
Like,
something more.
Like, I'm not too familiar with the internals, but like, at what level do you, like, if there are use cases where you had to add in a cache within the node, and that gets complicated if it's a distributed system. Because so like, what level of thinking, or like, were there any gotchas over there, or anything you ran into, or anything you can add to that?
Sure. So we don't have any distributed caches, so we don't have that problem. And the reason why we don't have that problem is because the scene is fast, first of all. And the second thing, on a single shard level search, you can create very efficient data structures that are cacheable. You know how the scene works under the scenes? The wonderful thing about that data structure, and obviously it was reinvented over and over again, like with level DB or something like that. This is one of the wonderful things that the scene had from almost day one, I think, is that internally, a Lucene index is actually composed of many small indexes called segments. They're almost completely self-sufficient. Completely, like if you take that segment and put it in another Lucene index, it will work. Self-sufficient. There's repetition, obviously. The terms or the cat will exist in each one or something like those lines. But they're immutable. And they don't change. And the bigger they are, the less likely they are to change. Because of, as if they are immutable, it means that you create those segments every time it runs, and then eventually you need to merge them to make sure that you don't have like many segments. And then it leads itself to very efficient data, like cache data structures. For example, one of the biggest problems with cache is invalidation. If someone just went in and updated the document with ID 1, a logical document ID 1, how do you go and invalidate the fact that it matches a specific filter if you have a filter cache? But you don't have to worry about it anymore in the scene because it just ends up being a re-index. So the old one still applies. There's a deleted document speed set that is being maintained properly and refreshed. But you don't have to go and invalidate that cache. So you don't worry about concurrency. A read in the scene has no locks. Not even a read lock, no locks. Just go and execute a read. So all of those things are very, very efficient and leads itself to building if you think about it, the right type of caching that you want to do. You want to build the caching in the most coherent manner that you can, and you can do that with Lucene. So we have those filter caches and film data caches and all of those things that enjoy the fact that the way that Lucene works, you can actually make use of it. And that is just super fast. And yeah, I don't know. That's effectively the only level of caching that we have in Elasticsearch. All of them are based filter caches or fill data caches that are just based on the fact that Lucene works like that. Yes.
So during the bulk indexing, so let's take the search request coming in. So basically, the search request will be opening up a new search or something, which may take a bottleneck on the search request. Right? So basically, how Elasticsearch is how my cluster has to be set up to avoid the search latencies.
So not bulk. You start with bulk indexing.
Yeah.
But you mean about search?
Yeah. So when there is a bulk indexing happening,
yeah.
So I should not hit on these searches.
Yeah. So what happens is that as you do bulk indexing and indexing happening in the scene, and that's great. You gotta run. There's a background thread in Elasticsearch that just calls refresh every 1 second or something along those lines. And that refresh in the scene effectively, what it does is it takes whatever in-memory data structures that the scene has, and flushes them to make them segments in a concurrent manner. So you can continue indexing while it's happening, and then reopens the searcher in the scene searcher, and then we just use that searcher through the searches. So it's just a matter of flipping a reference once that searcher is ready, and then new searches will start to use that searcher. And the old one, you do simple reference counting. The old one will end up being closed once all the other searches are done with it. Does that make sense? Yeah. So you don't have to reopen and create a new. Well, the reader in the scene is the more expensive one, right? Not the searcher. You don't have to reopen a reader every time you do a search. You do it in the background every second or something along those lines. Yes.
What is the underlying methodology or the secret sauce in the Elasticsearch compared to the other search? How it can make faster? Is it typically map reduce and the same approach, or what is the difference?
Well, I don't think anything specific was invented by building Elasticsearch. Okay. I think that the biggest secret sauce is that we have a lot of empathy to our users.
Okay.
Yeah, I don't think we invented any type of new algorithm or something along those lines or what have you. I think we're good coders, so we care about testing. One of the proudest things that I have that we have now in Elasticsearch, a lot of it thanks to Simon just pushing it, is the test infrastructure. Just randomize testing. If you have time, hit Berlin buzzwords and check. There was some talks about randomized testing, and go and do it in your application. It's just wonderful. I can spend some time talking about that if you want. But yeah, I don't think there's any special algorithm that we invented and nobody could figure it out or something like that. And now we have it. Yes.
Yeah, I have a question regarding to your access control. Because I know that Elasticsearch chooses not to do any access control because it's usually a layer. You usually want to have the application layer in front of it.
Yeah.
But then what I found is that I love the plugin system. So it's actually you can actually write a plugin that's a full search interface that user can use directly. But then because there's no access control, we cannot expose it to the user. So what is the rationale behind it, and what is the way to deal with it?
Yeah. Well, it's complex. Like, we think that if we're going to address security, we have to address it properly. So we will address it eventually as a company. But today, you either want to put your application in front of it or proxy in front of it at the very least, and then be very, very careful about what you expose to the outside world. I always feel much more confident if the application is actually there. And if you expose it through a proxy, then it's internally within your organization or something along those lines. At the end of the day, you should think about it like, would you take MySQL and expose it to the web? Probably not. So you should think about it like that. So even though it has HTTP APIs and RESTful APIs and it's JSON and it's nice and what have you, we do it not because we want web apps to directly talk to it. Just because it's easy to develop clients, easy to develop language clients to it. And what have
The
you.
reason why I wonder about the access control is because we also use MarkLogic. MarkLogic does very similar things. It also has the application servers where you can actually have applications running on it with the access controls. So you can control who access it, at which level. But then, unfortunately, I want to do the same thing on Elasticsearch so that you can have less applications to maintain.
I understand what you mean. So you're saying like MarkLogic went to a weird route, which is like you can build application that run within MarkLogic, like it's a mini Tomcat or something like that, whatever. I'm not a fan of that. So when the plugin system was developed in Elasticsearch was not to actually write applications in Elasticsearch. And I'll tell you why. Like what we found is that whenever people actually put a lot of logic into the plugin system itself, it ended up being a maintenance nightmare. It's just hard to figure out if something doesn't work. Is it because of Elasticsearch? Is it because of an application running out there that does like talks to a database or something like that? It's just hard to figure out what's going on. So yeah, and the plugin system is there. Well, first of all, because we designed Elasticsearch to be modular, so we like that. Like we can inject like crazy components that throw exceptions everywhere and things like that. But we want to allow people to extend it, but not in the sense of actually writing application next to it. Sure, I mean we have a very pluggable REST layer, so you can actually start to So I don't know. I think that at that stage it might make sense to actually have like your own application. A lot of times it's like we might break things, it might affect your application. Maybe you want to write code in a different language that you're more familiar with. I don't know. There's tons of reasons why, it might be more maintenance. There's simpler maintenance why when it comes to it.
Thank you.
Cheers. Yes.
So basically, like if your
no, go for it.
so if your statement is true, then it's possible that there's two more layers before like the traffic actually hits the Elasticsearch, right? You have the cache, you have the
which cache?
Some sort of cache, right?
Oh, okay.
Right, and then you have the application logic, and then that's sort of Elasticsearch, right? Is it?
Well, typically there's one, which is the application itself that talks to Elasticsearch. If the application does some sort of caching, then it tends to be the same. Like go to memcache if it's there, yes. If not, go to Elasticsearch. But the typical stuff. I don't know. Maybe you talk about HTTP caching, like Varnish or something like that.
Okay, but you do suggest that they have one layer before
Elasticsearch.
Okay.
Yes, I would definitely feel more.
But like, is it possible? Is it common that people actually put like memcache and the application on the same node, like or they sort of have
another machine?
Yeah.
For memcache?
Yeah.
Or, well, I've seen everything. But if I had to recommend something, then I think that in the long run, you're saving money in the wrong place. Because like if you go to now an overloaded system, it's going to be very hard to know, is it memcache? You might be able to easily say, is it memcache or Elasticsearch? But if memcache is overloaded, it now overloads Elasticsearch. So I would almost always recommend running Elasticsearch on its own dedicated box without anything else running next to it. Even things that you don't think about, like you can have an application that just crashes the file system cache all the time. So you make the file system cache in the machine useless, and Lucene and Elasticsearch relies a lot on the file system cache. So it's things that resources that we don't want to share. Yes.
I wanted to ask a follow-up question about Kibana. I want to use Kibana, but for similar reasons, I don't want to expose Elasticsearch to the users, the customers. And so how do I do this? I wanted to create an API layer for various reasons, not just security.
Yeah.
But if I give them Kibana, then they can really, I'm a web programmer. I know how to do these things, right?
Yeah.
How do I do that? Or what?
Is that customers or internally within your?
No, customers. customers, and I don't want the customers to be able to see each other's data. Okay, create indexes, but there's other stuff I want to do.
Yeah, I think Kibana is too open to put it in front of customers. It's okay to put it in front of internal users that want to explore logs or something like that, but you probably want to build your own visualization layer that would do that. It's not what Kibana was meant for.
Okay, what was it meant for?
Just exploring Elasticsearch, but not as a replacement for an actual application that is being built on top of Elasticsearch. So
because we saw it, we thought, great, this is a lot of work we don't have to do.
Yeah. We're started to work on Kibana 4. It might we're making it more modular and pluggable and different ways that you can be able to skin it potentially and things along those lines. Not necessarily because you want to expose it to the outside world. But one of the things that we're thinking about is maybe being able to embed parts of Kibana in your application. And at the beginning, we're not going to address what you're asking for. So the assumption is you're embedding Kibana or parts of Kibana within an application that is internal within your organization, something along those lines. At least that you won't have to be malicious, intentional malicious people trying to crash it or something. But we might decide also to have an option to embed it. It's based on users' demand, I guess. It's not easy though. It's not easy. Elasticsearch is so open that you can do bad things, right? And we continuously improve on it. But you can DDoS a system just by executing like crazy fuzzy queries or something, right? So you need to be careful. Yeah.
Do you ever think about to create your own DSL to perform the search query? Currently, it's like embed those query function inside the JSON document.
Yeah. So you mean like
say like for example, MapLogic use an X query to perform the search functionality.
Yeah.
Or like Neo4j, they have a
cipher language.
Yeah. Cipher language.
So I think that admittedly the query DSL of Elasticsearch is not formal to a degree. I don't know if that's the right word. It's probably the right. I would say that it maps very, very closely to the Lucene query API. So if you know Lucene, one of the reasons why, if you know Lucene, you know probably 70 or 80% of the Elasticsearch query DSL. This is like how you would write Lucene queries. This is how you do with the query DSL. What we try to do with our query DSL is to make it approachable yet programmable. So one of the annoying part in the query DSL is when you have to write it by hand, which is very tedious sometimes. Or when you try to read the output of a failed query and you see like this big chunk of text and you go, what the hell is going on there? But on the other hand, it's very composable. Like if you look at, I don't know too well about xQuery except knowing that it's very cryptic to me whenever I try to read it. But if you look at SQL, for example, what happened with SQL? People saw that they're writing programs and they don't want to concatenate strings. So you end up with ORMs that helps you write query builders that effectively build an AST that ends up creating these very long strings that represent a SQL query. So most of the times when you program and try to build a query, you want to work with like object-oriented type of elements in your search. And SQL is not meant for it, and that's why you have ORMs. And that's fine. Like I don't think that the other part of the O in the ORM actually works well. But I think that the part about actually programmatically building a SQL query in an object-oriented manner makes sense. And this is what Elasticsearch does. It's effectively an AST, and you can easily like, if you have all of your flow in the system, take a user input, maybe add this filter, another filter, or something along those lines. Those are like aspects of your code. This can go through the security layer and add the relevant filters for security, and then it can go through the time-based layer, and it can add the relevant filters based on time. And this is very easy to do with a query language. We can go and create something like Cypher, but we're the only implementation, so it's tricky. Yeah, I don't know. Clint had Clint from Pearl World created a very nice, concise version of the query DSL that works very nicely, like TPQL, TPQ, or something like that. The Pearl thingy that does something similar. I think that we will end up having to address it, at least the expressibility of it. But currently, the way that we look at it is we actually ask the users for too much in the query DSL. For example, why should you know about a query in a filter? Can we maybe remove that notion? Can we simplify some of the language elements that it has to make that more approachable? Still have it in AST, still have it like object-oriented and things like that, but just simplifies the core of the query DSL itself. Whether we're going to have something like Cypher or or SQL-based like thingy, I don't know. We might down the road, but we're not focused on it.
So since Shay has answered so many questions, so let's have the last question, and then he will stay a little bit longer. We still have more questions we can ask him offline.
Sure.
How do you come up with the names for the nodes?
Anybody else knows? How do we choose the names for the nodes? No, really? It's Marvel characters. So apparently there are many, like I think 3,000 Marvel hero names out there and villains. So we just randomized. I scraped the Wikipedia page and we randomized between them. And I did it before Marvel was successful. So what's there? I didn't bet on DC. Yeah, part of making the right choices.
Okay, so let's give our speaker a round of applause.